Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at the definition of the derivative. If you like this video, feel free to click the like button. You can comment in the comment section. You can also share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comment section of the intro video, including this one. Let's take a look at the key ideas for this worksheet. First, tangent lines are lines that are just glancing a curve. Moreover, an equation of a tangent line could be this point-slope form, where m, the slope of the line, is the derivative of the function at x1. Here, x1, y1 is a known point of tangency. And this tangent line is assumed to be non-vertical. Of course, if the tangent line was vertical, we would not use a point slope form. We would use the equation x is some constant, where the constant is nothing but the x value of the point of tangency. Let's try this first one. It says, given that the function f of x is 2x squared, find f prime of x using the definition of the derivative provided. So here, if you've done calculus before, you'll recognize that the definition of the derivative, it's nothing but a limit as an increment goes to 0 of a difference quotient. This derivative is computed at the arbitrary x value x, hence the derivative function will be obtained, a function that for each input x value, it returns the slope of a tangent line to the graph of y is equal to f of x at the x value where we evaluated it, provided, of course, that this limit exists. So for us, we should probably start by writing here that f prime of x is equal to, and we just write our limit, but now we're going to insert in for the numerator terms what would be specific expressions from function f. So f of x plus h, that will be 2 times x plus h quantity squared minus f of x, so that's minus 2x squared. In the bottom, we still have h. Now, when you're finding derivatives using the limit definition, do remember to continually write your limit as h goes to 0, or if you're using a different notation, limit as delta x goes to 0. Make sure you keep on writing the limit until you actually evaluate the limit. So it is a cardinal sin to drop the limit prematurely in calculus when writing a limit definition of a derivative. So here, we're going to simplify in the numerator if we can. Can you follow this computation? The squaring of x plus h times 2, it yields what would be a 2x squared. Also, there is 2 plus xh terms times 2. Hence, that's plus 4xh. And we also have a plus 2h squared. We take away from that the 2x squared, and this is divided by h. Please observe that there are some like terms. So here, not only are they like, but they are opposites. So that's 2x squared, and that's minus 2x squared. They're going to cancel. We can also divide out a single factor of h from the top and bottom. So this gives us the limit as h goes to 0. And when the dust settles and the smoke clears, simplifying, this gives us the limit as h goes to 0 of just 4x minus 2h. Now, this is a polynomial in the variables x and h. We can evaluate limits of polynomials directly by just plugging in. So replacing the h by a 0 gives us 4x. The reason we can do this is because polynomial functions have a property known as continuity. We've actually looked at continuity in a prior worksheet, and it's due to this property that limits our function values. Hence, the limit as h goes to 0 of the polynomial function 4x minus 2h is just a function value with the h replaced by 0. Now, we can check the validity of this work using higher level math. So in particular, we can use the so-called power rule. Let's go ahead and take a look. So f prime of x is obtained using the power rule as 2 times a 2 times x to the power 1, which is a 4x. So that agrees with the result that we obtained earlier using a different method. In this next part of this question, we're tasked with finding the equation of the tangent line to the graph of y is equal to f at x is 3, and write the equation in this slope-intercept form. Here we have the solution. We started with the point-slope form. We systematically replaced x1 by 3, y1 by f of 3, which is 18, and the slope of this line should be f prime of 3, which, using the result obtained above, is 12. Placing all these values in and solving for y, we get y is 12x minus 18. In this next problem, we're tasked with finding dy dx by using the definition of the derivative, and our function is y is 1 over x plus 1. Now, all this work, we want to justify where it came from. So let's start from scratch to take a look at how it comes about. So this is what that will look like once we've divided out the h's. The last thing to do is to pass the limit as h goes to 0, and we get our final result. So here, it's going to be minus 1 over x plus 1 squared. Notice that we pass the h to 0 in that first factor in the denominator, so we can drop that term. Here, we can't check the work. So the derivative with respect to x, so f prime of x, it is verified using slightly higher level differentiation techniques. We can pull down an exponent of minus 1 and get x plus 1 to the power minus 2. That's in agreement with what was obtained. So this validates our calculation. Okay. Now, the other part of this question was to find the equation of the tangent line at x is equal to 1. So what we'll do is we'll write a blueprint for that tangent line equation. We have y minus y1 is m times x minus x1. And we'll just systematically start sticking in the values that we know. For x1, that was the value 1. So y1 should be f of 1, which in turn is equal to 1/2. And m here should be obtained as the derivative at 1, which is equal to, from our calculation, -1 over what is 2 squared. Okay, so that is a minus 1/4. We can now write our final version. We're not told what form to put the equation in, so we'll leave it in point slip form. It's y minus 1/2 is equal to a -1/4 times an x minus 1. And that's a good way to leave our answer. So that would be the tangent line. So here in this last example, we're asked to use the definition of the derivative to find dy dx at x is equal to 100. Let's use the color green for this. So first we'll find f prime of, well, I was going to say we could go for f prime of x, but why don't we go for f prime of 100 right off the bat? So this is the limit as h goes to 0 of, and our difference quotient will have the x replaced by 100. So it's f of 100 plus h minus f of 100 over h. In this way, we won't get the general derivative of the function y is root x, but we'll just get the derivative at x is 100. That's exactly what we needed for this question. So we should keep on writing the limit until we evaluate the limit. And we'll go ahead and write the expressions using the function for f of 100 plus h. So that would be the square root of 100 plus h. And this is take away the square root of 100. It's very important with your mathematics to be organized and neat. So the less organized we are with our work, we're more likely to make human errors. So you want to be extra meticulous in your structure and form when writing solutions to math problems, when doing mathematics in general. The longer the problems, the more of the impact there is when you do not write neatly, because it's just more likely that you make a tiny blunder that can then propagate and nullify all the work that you do. So here, to evaluate this limit, you can see that it's an indeterminate form. So this limit is giving us one of these like 0 over 0 expressions. So we need to use some sort of algebraic trick. I believe what we can do is we can make use of that conjugate expression. So I'm going to go ahead here, not use red. And this is what that looks like when we have used the fact that the function is equal to root x and replaced x by 100. I took the liberty to extract the square root of the 100, writing that as 10. You cannot similarly simplify the square root of 100 plus h because roots do not distribute across an addition or subtraction for that matter. So what we need to do next is try to find a way to evaluate this limit, which is on the surface giving an indeterminate form. The numerator and denominator are both racing to 0. Who's going to win the race? I believe the algebraic trick to evaluate this limit is to use the conjugate. So we'll multiply by 100 plus h in root plus 10. So that would be the conjugate of the numerator expression. And in the bottom, we have likewise h times this square root of 100 plus h plus 10. And if all goes well, we'll be able to cancel out the h's. Let's see if that is the case. So we'll make a little more space to work. We have the limit as h goes to 0. So notice in the numerator, when you multiply that two-term root expression by its conjugate, there is some simplification. The outside product and the inside product are going to be opposites. We have the product of the first terms is just the quantity inside the root. Outside and inside products are just opposites of each other. It's plus or minus 10 times this messy root. And the last product is minus 100. It looks like I didn't need such a big fraction bar. So here we can go ahead and make that a little nicer. There we go. And in the bottom, we have what is h times that conjugate factor again. So 100 plus h plus 10. Well, we can simplify. We can simplify that 100 and this minus 100 are canceling. And then sure enough, we can divide out a factor of h. And we may even be able to see that passing the limit as h goes to 0, you'll be able to here take the root 100 plus h in the denominator and kind of swap that out with root 100 because h is going to 0. So this gives us, when the dust settles and the smoke clears, a 1 in the top. And in the bottom, we find in the bottom just the square root of 100, which is another 10 plus 10. So we got 1 over 20. We should check the work here using an independent method. So using what would be the power rule, f prime of x, the derivative, is going to be 1/2 times x to the minus 1/2. And that means that f prime of 100 is going to be 1/2 times what is 1 divided by the square root of 100. That is indeed 1 over 20. So that, again, is an independent validation of our work. So this validates our work. And with that, we have solved yet another calculus worksheet. This one on the limit definition of the derivative. We know there are quicker ways to find the derivative, but it's fundamental that you understand in calculus that derivatives stem from limits of difference quotients. And these were the types of calculations that we did in today's activity. I hope you enjoyed this video. Feel free to click the like button and subscribe. Share the video with your friends and classmates if you think it'll help them. And I look forward to solving more worksheets with you in future videos. Bye-bye.